Hi there, it's Mrs. Dinkelman again, and we are doing the AB review applications of derivatives. This is really the two main word type problems that we'll see in calculus. So one is related rates and the other is optimization. So we'll focus here on related rates and then we'll do optimization here in a second. So you can see there's a definition there for what a related rate really means, and it's that the rates of the two things that we're talking about are somehow related mathematically. So we can use one really to find the other. So the steps, at least in my mind, as I'm trying to find them, we want to decide on a formula that best fits that situation. So whether that be like a Pythagorean theorem or an area of something, we want to take the derivative implicitly. We're going to do that with what method I say. It's my method because I do implicit a little bit different. So we're going to see those DTs there as well. Sorry if you hear the noise in the background, it's my kids. Then we're going to substitute the known information in before we solve, and don't substitute in until the end, except for if it's something that's true for all time. Excuse me. For instance, in example 1 here, we have a 10-foot ladder. That ladder is a ladder that does not, it doesn't shrink and it doesn't collapse on itself. So that ladder, we can substitute that information in if we would like. And then it's always helpful on a free response to not forget your units. Sometimes units are worth a point, so it's kind of a irritating point to lose, but nice if you're not really quite sure if you know what you're doing, you can maybe include the units. Okay, so example 1 here with the ladder, pretty typical problem. And just a note here that with triangle problems, we're probably going to either use Pythagorean theorem, some type of trig equation, that's if they give us some sort of angle of elevation or something like that, or a similar triangle setup. That's like the light post problem with the shadow, for those of you that remember that type of problem. Okay, so on this particular ladder problem, we are going to use Pythagorean theorem, and I'm just going to go with x squared plus y squared equals z squared. And I know I shift this and then my webcam doesn't work, but I can't write unless I have it just the right way. And actually, this ladder is the part that I was telling you that you could plug in. It's 10 squared. So we can just plug that in right away. If you don't and you forget, when you have a dz dt there, that's the rate at which the ladder is going to be changing, and it's not. So then dz dt would be 0. So if you just forget, it's always okay to put that the rate is 0. Okay, so that's the formula we're going to use, and we're going to go ahead and take the derivative implicitly. And when I do implicit, what I do is I do a 2x and then I put a dx because we took the derivative of something with an x. That might be a little bit different compared to what you've done in the past. 2y, that's a dy because we took the derivative of a y. So now that I know it's a related rate, what I'm going to do is I'm going to divide by dt because those are the rates that we're going to talk about here in a second. You'll also notice that I didn't really totally read the problem very well. So I'm going to have to go back and see which of these things I have. So I have a ladder that's 10 foot. You might do this at the beginning. For some reason, I tend to do it later. It slides away from the wall at 1 foot per second. So that's this part that they're talking about. That's going at 1 foot per second. How fast is it dropping down? So we're looking for this rate. And then we're talking about when the ladder is 6 feet from the wall. So I'm going to go ahead and put that in here now because we're going to use it. This must be a 6, 8, 10. I'm just thinking of the 3, 4, 5 and doubling it, but we could also do Pythagorean theorem to figure that out. So I'm just going to consider this part to be x here, this horizontal part, and the vertical part to be y. So the x is a 6, dx dt is 1, y is an 8. We're looking for dy dt. Hopefully, if we look back at the question, it's asking us how fast it's sliding down or something like that. So I think for dy dt, we're going to get, let's see, if that moves over, that's going to be negative 12 and over 16. So we could simplify that, negative 3/4. And let's see, this must be feet per second. Now let's just pause for a second and make sure that negative makes sense. And it does make sense because since this is sliding down the wall, the distance is getting shorter. So that makes it a negative rate. Okay, this next one, example 2, is also a really typical problem. And it's because they want us to kind of change the variables in there and not have to do a product rule. Normally they include the volume here. So the volume of an inverted circular cone, so it's upside down, it's circular because there's not like an ellipse on the bottom. The volume is 1/3 pi r squared h. So because we have r squared times h, we would have to do product rule to find the derivative, which makes life difficult. Sometimes that's okay because they give us lots of rates in the problem, but in this case, as I'm glancing, it only gives us one rate, and so that's not going to be enough. There should be some information so that we can just get this down to one variable here. So they're telling us that, let's see, the base of the cone has, let's see, radius 2 and the height is 4. And so what I'm going to do is just write a radius to height ratio here. And so basically what we're finding out here is that the radius is always half the height, because this is just a similar triangle idea. In a cone, the radius to height ratio should always be the same. Okay, so let's just kind of read here. It looks like it's talking about the water level rising. So it wants us to keep the h's in there and replace the r's, which is fine because that's how I have that set up. So let's go ahead and rewrite this volume. So instead of r squared right here, I'm going to insert this 1/2 h. And let's go ahead and simplify before we take the derivative. So again, we don't have to do product rule. So this is going to end up being 1/4 times the 1/3, and then I'm going to leave that pi in with there. So pi 12ths, and it's going to be h cubed. This derivative is going to be a lot nicer. So I'm just going to call that 3 pi over 12 for now. And then we'll divide by our dt's. And then we can start plugging in. So let's see here. Water is being pumped into the tank at 2 meters cubed per minute. This tells me dv dt because I see the cubed here. And let's see, I'm going to go ahead and simplify that. That's pi over 4. It wants to know what's happening when the water depth is 3. And so now all we have to do is solve. So let's see here. We're going to have a 2. Let's see, this is going to be 9/4. So if I multiply on both sides, the 4 is going to end up being on the top, 9 pi on the bottom. So basically 8 over 9 pi. And let's go ahead and sneak a label in there. It's meters per minute because height would just be in meters. Okay, so as I mentioned, the other type of word problem is the optimization, where we're really just looking for a max or a min. And a lot of times in this one, there's two kinds of equations. There's the extrema, the thing that we're trying to find the min or max of, and there's the constraint, the thing that tells us, oh, we only have so much material or something like that. Nolan has a question for me. Hi, Nolan. If you can come in the video, yeah. You're not going to see yourself, but it is on. You can say hi. Hi. What do you need? Okay, all right, I'm just going to keep going with the notes, okay? So again, you're going to have two equations that you might have to deal with. Sometimes it just kind of comes naturally and you figure out what's going on with them. So for example 1, oh, and by the way, take the derivative, just be worried about domain there. Sometimes you'll get some derivative equal to 0 that doesn't make sense as part of the problem. You can kind of throw those out. So example 1, find two non-negative numbers whose sum is 9 and that the product is maximum. So you don't really have to follow along with my extrema and constraint if you can kind of make this work. But the constraint is going to be the fact that the two numbers have to add up to 9. Okay, so I know it has to be two special kind of numbers. And the thing I'm trying to maximize is this thing. The product, I'm just going to call it P equals for product. Product of one number and the square of another, okay? So this is the thing that we're eventually going to try to take the derivative of and set equal to 0 because we're looking for a maximum. Right now it's two variables there on the right-hand side and we don't want that. So we want to make sure that we substitute. So I think the easiest thing to do in this problem is solve for the x. We'll call it 9 minus y, and then we'll come up here and we'll rewrite this p. So we're going to have 9 minus y times y squared. And because we're going to take the derivative of this, I'm going to go ahead and just simplify it a little bit. You're welcome to use your calculator on these that kind of turn out. Sometimes they're not so nice. So if you need a calculator, feel free. I usually try to do it without, and then if I feel like I get stuck, then I'll go with it. Okay, so we take the derivative. We're going to set it equal to 0. So I'm going to just factor here a little bit so we can see where it's equal to 0. So that's when y equals 0 and 6. 0 doesn't really make sense because that's really not going to maximize my product. So it's probably 6. Sometimes it's helpful just to double check that this really is a maximum. and I'm going to stop at 0 because it said I don't want it to be negative anyhow. Just to make sure that this does go from a positive to a negative. So let's just check that. So 2 here, yep, that'd be positive times a positive. Let's pick 8. 8 would be a positive times a negative. So yes, it makes sense that this is where my maximum occurs. Now don't forget to go and answer the question. So it just says find the two numbers. So we have one of the numbers, so 6. And then based on this information, the other number must be 3. Okay, example 2. So we have a rectangular pen with 3 parallel partitions. Let's see. So something like this, I guess. We're going to use 500 feet of fencing, and we want to maximize the total area. So to me, this 500 feet of fencing, that's really the constraint, and that's really the perimeter. So I'm going to call this, let's go, this is X and X and X, and then we'll call this Y. Maybe I shouldn't do it all the way across. Let's just have it be 1x. So otherwise that's going to be a lot of variables in our problem. It doesn't want to erase right now. Come on. Okay, we're just going to pick a different color and say, okay, let's go x all the way across. And maybe in a second it will let me erase. We'll just do it that way. Okay, so we're going to say here that 500 feet of fencing, there's going to be 2 x's. And then there's going to be 1, 2, 3, 4 y's. I'm pausing for a second, making sure this 3 parallel partitions makes sense. I really only have 2 partitions. I'm trying to figure out if that's what they want. Normally on this type of problem, what they're going to do is they're going to give you a picture so that you can make sure that you have the exact right thing. I'm going to go with what I have, but it could be that we need another one in there, so feel free to do it that way as well. But we'll get at the idea of it anyway. Okay, so that's our perimeter, and we want to find the maximum total area. So the area is what we're going to take the derivative of. So we're just going to call that xy. And again, we want to get rid of a variable here. So let's just solve for x, I guess. So it's going to be 500 minus 4y, and we'll divide that by 2. And actually, since they divide nicely by 2, that makes this easier. So instead of an x right here, I'm going to put 250 minus 2y, and then times y. And again, we're going to want to take the derivative of this. I'm kind of running myself out of room here. So I'll come over here. So a prime now, 250 minus 4y, we're going to set that equal to 0. So we're going to do 250, oops. And what is that? So it's going to be, well, it's not going to come out nicely, is it? Oops, divided by 4. So it's 125 over 2. That might be not a nice, because I didn't do 3 parallel partitions. I really only did 2, but we'll go with it. So that's what we think our y is. What are we looking for? We're looking for the dimensions. So right now what we have is that we have a 125 divided by 2. So let's see. I'll just leave it at that. And let's see, that's going to be feet by, and let's see what the x is going to be. How easy is that going to be for us to do? So probably would be nice to have the calculator right now. I'll let you go ahead and do that on the calculator and figure out what that is. And then real quick wrap up before you move on to the assignment, and maybe I'll see if I can grab my calculator while we're having this chat. So how do you tell the difference between a related rate and an optimization problem? So that's something I want you to think about. Oh, there is my calculator. Okay. Oh, nope, it doesn't want to work. So how do we tell the difference when we're looking there? And one of the ways is just to look for that word rate, or to see the that there's like meters per minute or something like that. That would mean it's a related rate. Another way is to look at whether they have talked about maximum or minimum in the problem, or look for those words that kind of mean maximum and minimum. So that's one way to do that. So I can see that my calculator is not going to work. So finish up that example, make sure I have that right, and then try to think of some ways that that you can tell the difference between related rates and optimization, and go ahead and keep working and get to the assignment.